Guys, glad to see you back for part 2 of Chapter 13's exciting notes. And I think we're liking Chapter 13 a lot better than the previous chapters because the math is like I said in the previous one, it's just a little less complicated, a little less going on. All right, so I'm going to pick up in your notes where you have this next example. And in this next example, you are looking for molarity, molality, and weight percent. And you're given some stuff. So just to kind of get myself straight, I'm going to write some notes for me. All right. Molarity is moles over liters. Molality is moles over kilograms, right? And weight percent is going to be the grams of the solute over the grams total. And because it's a percentage, I'm going to go ahead and multiply that by 100. And that's going to kind of keep me straight in this problem. So I've got 17.2 grams of ethylene glycol and 0.5 kilograms of water. The final volume of the solution is 515 milliliters. All right, so I'm going to start first by finding the number of moles, okay? And I know that I have 17.2 grams of this ethylene glycol. Oh, sugar. Okay? And just because I've been brainwashed because I'm a super chemist, when I see that, I automatically just want to convert back to moles. So I know that from the happy cloud last year, moles is always going to get 1. Grams comes from the periodic table. This should be super easy for you guys. You should be able to go ahead and just convert that right away. All right? So I'm going to start with molarity. Molarity is moles over liters. Well, that's how many moles I have. That's why I converted it right away. All right. When you look in the problem, it says you have 515 milliliters of solution. All right. All I'm going to do to that is divide it by 1,000 or move the decimal place over and put that in liters because that's what I need for molarity. I need moles over liters. All right. Put it in my calculator. The molarity is 0.54. I put a biggie M after it to show that it's molarity. Easy peasy, I'm done. So now I'm going to the molality part of the problem. And molality is moles, again. But this time I'm over kilograms of water. In the problem, you were given 0.5 kilograms of water. 0.5 kilograms of water. Easy peasy. Plug it into my calculator. 0.55 molal, or little m, okay? And then the last thing we're going to do is weight percent. So I know that I have 17.2 grams of solute. All right, that's how the problem starts out. Okay, got to have it over the total grams of everything. So that's going to be 17.2, and it's going to be 500 grams of water. How did I get 500 grams? Because I told you I had 0.5 kilograms. So I move the decimal over, multiply by 1,000, and I get 500 grams. All of that times 100, 3.3%, and I'm good to go. Yes, that was a lot of work for one problem. Boom, boom, boom. Was any of it really hard? Not at all. You could have handled that last year in high school chemistry. All right. So last year we briefly, and I do mean briefly, talked about colligative properties. And we said if you add a solute to water, it brings the boiling point up. It's called boiling point elevation. If I add salt to my pasta water at home, the boiling point goes up from 100 degrees. If I put salt in ice, the temperature drops below 0. And that's how we make ice cream, right? All right, well, there is, and I think we looked at it, but we never really did much with it last year. There is an actual formula that we can determine the exact amount that we are going to lower that freezing point or elevate that boiling point, okay? And the formula, again, is super easy here. Change in temperature. How much am I going to change that temperature from 0 degrees for freezing? Times K. K is some constant number I have to give you. It's not something you memorize. Times molality. All right? So what I did here is I gave you a little example. What is the freezing point of a 1.7 molal aqueous solution of ethylene glycol? All right. The K value is 1.86. The molality is 1.7. That means that I'm changing the temperature of the freezing from 0 degrees, but I'm dropping it by 3.2 degrees. So what's the actual freezing point now? The actual freezing point is no longer 0. It's 0 minus 3.2 because it's going down. So the new freezing point is negative 3.2 degrees Celsius. I do expect you to know that the freezing point of water is 0 and the boiling point is 100. You should already know that, okay? That's nothing new and exciting. I did go ahead, and I know it's in your book, but in your notes, I did put a little table of freezing point, depression, and boiling point elevation constants. On a test or quiz, they would be up in the question for you, so quick and easy, you could just pop out your answer, okay? Now, would I maybe be evil and put both the freezing point and the boiling point numbers in there to make you really look at it? Probably, okay? So boiling point elevation is the same way. Delta T equals Km. And say for a particular solution, you do this problem and you find out that delta T for boiling point, the change was 1.2 degrees Celsius. If I asked you what the new boiling point would be, I know that the boiling point of water is 100. If it's going up by 1.2. So the new boiling point would be 101.2 degrees Celsius. All right. The last thing I want to talk to you about today is calculating osmotic pressure. All right. And you'll notice when you look at the slide, you know, I wrote the formula, I wrote what everything is. And so osmotic pressure is represented by pi. Don't get that confused with pi in math class. Equals capital M. What do you think capital M is? Capital M is molarity. Okay? Then I have an R value. What's R? R is good old 0.0821. And T. T is temperature. Temperature has to be in kelvins. Okay? I would give you all of these and you would solve for one of those as your X. The example here. The osmotic pressure of a solution containing 5.8 milligrams of an unknown protein per 10 milliliters of solution is 2.45 torr at 25 degrees Celsius. Find the molar mass of the unknown. Okay, so I know right away that the pressure is 2.45 torr. It has to be in atmospheres for this problem. So probably one of the first things I'm going to do is go ahead and convert that pressure. And I know that ATM gets 1, torr gets 760. So that pressure is going to be about that many atmospheres. All right, so I'm going to go ahead and put this right on in here. Now, I don't know the molarity. So that's going to be my X. R is that number. The temperature is 25 degrees Celsius. What do I need to do to it? That's right. Add 273, make it Kelvin. All right. This is an easy algebraic equation for you to solve. Solving for X should not be an issue for you guys. When I solved for X, I got something that looked like that. You should be somewhere in that ballpark. Well, that's fine. That's molarity. Okay, I asked you for molar mass. And I know that molar mass is equal to grams over moles. Well, in the problem, I gave you milligrams. So you're going to have to convert milligrams to grams. And when you do that, you had 5.87 milligrams. That becomes 5.87 times 10 to the negative 3 grams. So what I'm looking for now are moles. Okay? Now, I know that I have a 10 milliliter solution, okay? And I know I can convert milliliters to liters because that's easy. Why did I convert it to liters? Because I'm looking for moles, and I can convert liters to moles using the molarity I just found. Okay? When I put all of that in my calculator, I have 1.3 times 10 to the negative 6 moles. I need that for my molar mass because molar mass is grams over moles. So I'm going to take that number, put it in there, and you kind of get a big molar mass. But, you know, it said it was a protein, so maybe it's a biggie protein. Okay? That concludes your notes on Chapter 13. I hope they help you out. Come see me in class if you have questions. Woohoo! Almost Valentine's Day. Toodles poodles. Bye.